Hello everyone, welcome to the class once again. I hope you are doing good and in the best of your health. In the last class we were talking about the first 5 questions on this chapter thermodynamics, and we practiced question based upon JEE Main pattern exercise. JEE Main examination, that is single choice question, will be getting 30 questions and each chapter will be having some question based upon it. This is very important chapter thermodynamics and we have discussed some good questions based upon this chapter. Let's go with the next 5 questions of this session and the first question of the class. Question number 6. 5.6 liter of helium gas at STP is adiabatically compressed to 0.7 liter. Taking the initial temperature to be T1, the work done in the process is A 9/8 RT1, B 3/2 RT1, C 15/8 RT1 and D 9/2 RT1. It says that you see 5.6 liter of helium gas. So let me tell you 5.6 liter of helium gas at STP, you must be knowing that 22.4 liter is equal to 1 mole of any gas kept at STP. So 22.4 liter is 1 mole. So how much will be 5.6 liter? 22.4 liter is equal to 1 mole at STP. Remember, this is valid at STP. We all know this. That is why STP is given. So 5.6 liter. Therefore, 5.6 liter will be equal to 5.6 multiplied by 1 divided by 22.4. That is equal to 1/4 moles. That means the gas contained within the container, that is 1/4 moles. Next thing you see, it is compressed to 0.7 liter and the system has gone through an adiabatic process. It is adiabatically compressed to 0.7 liter. We all know in the case of adiabatic process, PV power gamma equals to constant. So if you see PV power gamma is equal to constant, so how can we find out the final temperature that it is attained? There's nothing given about the initial pressure, but the volume difference is given with the final volume and initial volume. Nothing is talked about the initial pressure. We all know that PV equals to nRT, and suppose you want to write the same adiabatic equation in terms of temperature and volume, you can convert it by using pressure as nRT by V, and from here what you do, you put this value here, nRT by V, that is if suppose here you see n is constant, R is constant, pressure will be proportional to T by V. So what I'm going to do, I'm going to put pressure is equal to T by V here. So from there we can get the how the adiabatic equation will hold in terms of temperature and volume. So let's put pressure is proportional to T by V because N and R are constant. So keep pressure here as T by V, you will be obtaining T by V, V to the power gamma is equal to constant K, and finally it will come out to be TV power gamma minus 1 is equal to constant K. Now next thing you see here, it's given that it's a case of helium gas. Helium, that's a monoatomic gas. Let me write down separately, it's a helium gas. It's a monoatomic. From monoatomic, you must be knowing what value of gamma should be supplied. So gamma in the case of monoatomic gas is Cp by Cv, and that is actually 5/3. This is what we know about the gamma of monoatomic gas, that is adiabatic constant. Now initial volume is given. Initial volume is given as 5.6 liter, and final volume is 0.7 liter. That is what has been provided. So how the temperature will be actually given? You see here, taking the initial temperature to be T1. Taking the initial temperature to be T1, in terms of T1 we have to answer. So what do you do? Taking the initial temperature to be T1, so we can write T1 and initial volume as 5.6 liter. You can see that it's 5.6 liter of helium gas. So what do you do? T1 into V1 power gamma minus 1 is equal to T2 into V2 power gamma minus 1. This is what we can use, the constant for the adiabatic relation. T2 is equal to T1 V1 by V2 power gamma minus 1. T1, in terms of T1 we can find out the value of T2, that is the final temperature it has attained. That will turn out to be V1 is the initial volume and V2 is the final volume. So 5.6 divided by 0.7 power 5/3 minus 1. easily you can evaluate. This will go 8 times, you will get T1 into 8 to the power 5 by 3 minus 1, you will get 2 by 3. 8 to the power 1 by 3 will give you 2, 2 to the power 2, 4, so this will come out to be 4 T1. I believe that you can clearly see that T2 equals to 4 T1. First thing we obtained the value of T2 in terms of T1. Next thing you see what we need to do. Taking the initial temperature to be T1, the work done in the process is, we need to find out what is the value of work done. In an adiabatic change, in an adiabatic process, the heat energy supplied is 0. Let me rub this part, it's not required anymore. Remember 1 by 4 moles is the number of moles of gas that is in the container. For adiabatic process, we know that delta Q is 0. For adiabatic process, we know that delta Q is equal to 0. This is what we know. Next you see that we can use the first law of thermodynamics equation, because that will be also holding delta Q is equal to delta U plus W. If this is 0, we will get W is equal to minus delta U. And I have told you about with respect of degree of freedom what will be the value of delta U, that will come out to be N F by 2 RT. This is what we can say. Or before that, let me tell you about, it is NCV delta T, NCV delta T, that is what we can comment on the value of delta U. We can write in this way, and minus here sign was there. N is 1 by 4, that is given. CV, that can be written as R upon gamma minus 1 in terms of R and gamma. CV is can be written as R upon gamma minus 1 into delta T. This is what I can write, this is what we can reach to. And now you just substitute the values. You substitute the value N as 1 by 4, gamma as 5 by 3, that I already have told you. This you do, and delta T will come out to be T2 minus T1. You will get the answer. So finally you see what I am going to do. See here, N is how much? Let me write down here, delta U is equal to minus, and before that you see W equals to minus delta U, I have already applied here. So let us use directly W, that will give us the work done directly. Work done is equals to minus N as 1 by 4, and then R upon gamma minus 1. R upon gamma minus 1, keep here R upon gamma minus 1, 5 by 3 minus 1, multiplied with delta T, T2 minus T1, that is what we can do. So let me rub this part, we have already used this, into T2 minus T1. T2 is actually 4 T1, that is what we have reached. So finally we are going to get minus 1 by 4 R, and this will give us 5 by 3 minus 1, so 2 by 3. So this will become 3 R by 2, and T2 minus 1 will give us 4 T1 minus T1. This will give us minus 4 T1 minus T1 will give you 3 T1. I am writing directly 3 T1. Now easily you can evaluate it, minus 9 by 8 RT1. This is the value of W, the work done. The work done turns out to be minus 9 by 8 because the gas is compressed. So minus 9 by 8 RT1, that is what we are finding. Now one more thing, try to understand. The answer comes out to be negative, that is the actual, because the gas is compressed, you are doing work on gas, answer has to come negative. In our case, it's only given the magnitude. So you need to check which magnitude suits with the best option. Option number A, 9 by 8 RT1, yes, this is the right magnitude. This will be the right answer. Rest 3 by 2 RT1, no. 15 by 8 RT1, no. And 9 by 2 RT1, no. If smartly you proceed with each of the basic steps, you are going to find the right answer for such questions. This is a very good question asked in a previous examination of JEE. If you are thorough with each of the basic things, you can easily solve them. But yes, you can see that there are a lot of steps involved. Until and unless you practice at home, you cannot excel on the day of your examination. You require practice so that you can directly input these steps, you can follow these steps, and you can reach to the result. So very good question. I believe that you have understood each part of it. And let us proceed with the next question of the class and the 8th question of the session, 7th question of the session. 7th, two monoatomic ideal gases at temperatures T1 and T2 are mixed. There is no loss of energy if number of their moles are N1 and N2 respectively. The temperature of the mixture will be A T1 plus T2 divided by N1 plus N2, B T1 by N1 plus T2 by N2, C N2 T1 plus N1 T2 divided by N1 plus N2, and D N1 T1 plus N2 T2 divided by N1 plus N2. See, at two monoatomic ideal gases at temperature T1 and T2 are mixed. There is no loss of energy if number of their moles are N1 and N2. Now see, when let us say the total number of moles combining the two will be N equals to N1 plus N2. That is quite obvious. This is what we know, N equals to N1 plus N2. Now when they are mixed, there is no loss of energy. There is no loss of energy. So change in internal energy, we need to find out the temperature of the mixture will be. See here, the change in internal energy, that will be equal to change in internal energy of first plus change in internal energy of the second. That is what we can comment on. Next, you see the temperature of the mixture we want to actually comment, and before change in internal energy is not required, you can write down the internal energy of the mixture is equal to internal energy of the each of the gases that we can comment on. We all know that internal energy can be written in terms of CV. So N CV and into T is equal to, this is N1 CV. It says the two monatomic ideal gases, so monatomic, so CV will be same, T1 plus N2 CV T2. We can comment in this way. We need to find out the value of T. Rest you see T, how we can find out? CV will be cancelled out. Monatomic gas, CV will be same. So that's why I have used the same CV everywhere. CV will be cancelled out. So T will come out to be N1 T1. You can see here it will be N1 T1 plus N2 T2 divided by the number of moles, that is N. Now before commenting on further answer, what you do, take note till here so that I may write till the other end. Take note till here. Okay, now you see the result we have arrived at. Now you have to substitute the value of N as N1 plus N2. So final value of temperature will come out to be, it will be equal to N1 T1 plus N2 T2 divided by N1 plus N2, because N is equal to N1 plus N2. That is what we have already noted down. So the result that turns out to be, this is the value of temperature N1 T1 plus N2 T2 divided by N1 plus N2. Let's go ahead. Option number A, T1 plus T2 divided by N1 plus N2, no. Option B, no. C, N2 T1 plus N1 T2, no. And D, N1 T1 plus N2 T2 divided by N1 plus N2, yes. Option number D correctly matches. So this is a very good question in understanding the concept of internal energy and how it is dependent on temperature. I have told you about the internal energy dependence on temperature. I have explained it with respect to degree of freedom also. Let's go ahead and let me tell you U equals to N F by 2 RT, that is also you can also use in this case. 8th question, this is a good question. An ideal gas is taken through the cycle A, B, C, A. So A to B to C to A as shown in the figure. If the net heat supplied to the gas in the cycle is 5 joule, the work done by the gas in the process C to A is A minus 5 joule, B minus 10 joule, C minus 15 joule, and D minus 20 joule. So you are obtaining this. You see what is happening, an ideal gas is taken through cycle A, B, C, A. This is cycle. You have to find out net heat supplied to the gas is 5 joule. So let me tell you, the heat energy supplied is taken as positive. Delta Q is equal to plus 5 joule. That is what that has been given. The work done by the gas in the process C to A. C to A process, what is the work done by the gas? So what we can do, we can use that delta Q is equal to work done by the gas during all these steps, and then we can also use the changing concept of internal energy. Since the process is cyclic process, it's A to B to C to A. A to B to C to A, it's a cyclic process. Cyclic process, what does that entails to us? Delta U will be 0. If delta U is 0, that means we know from first law of thermodynamics, delta Q is equal to delta U plus W. So therefore, as delta U is 0, so delta Q will come out to be work done. Next, you see work done for the entire process can be written as work done during A to B, work done during B to C, work done during C to A. So we can write this as this is what we can write. Next, work done during A to B. A to B, you see that pressure is constant, volume is changing. So we can use 10 Newton per meter square, that is given in standard units, multiplied with volume is given in standard units, that's the change in volume is 1. So this will come out to be 10 into 2 minus 1. So I am writing it separately here for A to B. Work done during A to B is equal to P delta V, and that is 10 into 2 minus 1 with proper units come out to be 10 joules. Now work done during B to C, you see here what you are going to get during B to C. Here the volume is constant, so volume is constant and no work is done. So for B to C it will be 0. We need to find out for the value of C to A. So from this first equation, work done during C to A will come out to be delta Q minus WAB minus WBC. Delta Q minus WBA minus WBC, this is given as 5, this is comes out to be 10 minus work done. This is not BA, this is AB. I have written BA, this is AB, so this is 10 and this is 0, this will come out to be minus 5 joules. That is work done from C to A is minus 5 joules. So we obtained this. Quite simple and clear to us. I believe that you have understood this. Minus 5 joules. So let me mark this as the right answer. Minus 10 joule incorrect. Minus 15 joule incorrect. Minus 20 joule incorrect. Hope that you have got. Next thing. This is an easy question, and how to use the graph. This has let us understand. I hope that you are understanding which each of the question, what kind of question can be raised in your JEE examination. Let's go ahead with the next question of the class. Now you see that what I want from you all. If you prepare each of the concept, if you have gone through basic detail, if you have practiced question, it will be of no difficulty for you all to solve questions. Each basic steps is required. Let's see question number 9. Two cylinders A and B fitted with pistons contain equal amount of an ideal diatomic gas. Two cylinders contain equal amount of an ideal diatomic gas. Let me first try to make a diagram from the first given information. Fitted with piston, so I have taken two cylinders fitted with piston. Ideal diatomic gas is actually filled in both the two. A and B are the two cylinders. That is what that has been given to us. Same amount of gas we have taken. That's why I am drawing in similar fashion both the diagram. Diatomic gas. I hope that you must be remembering the Cp and Cv value of it and the gamma value of it. So this is piston cylinder B. Now you see what is required in the question. It says that, and it is kept at 300 Kelvin. Two cylinders A and B fitted with pistons contain equal amount of an ideal diatomic gas at 300 Kelvin. The piston of A is free to move. The piston of A is free to move. This can freely move. This is free. Next, while that of B is held fixed. B is held fixed. That means its volume will remain constant. It is fixed. delta V is equal to 0, volume will never change, it's fixed. So that's why I have written delta V is equal to 0. The same amount of heat is given to the gas in each cylinder. You have provided the same amount of heat. Let's say the same amount of heat is delta Q in this and delta Q in this also. We have made it. If the rising temperature of the gas in A is 30 Kelvin, then the rising temperature of the gas in B is. How to use it? Now see, when you supply heat energy to this, it's free to move. For A, whatever heat energy you are supplying, the pressure will remain constant. You can easily understand, because it's free to move, the pressure will remain constant, that is the atmospheric pressure. So for A, delta Q will be equal to N Cp delta T, and for B you see, you are giving the same amount of heat energy, you have held the fixed piston at the fixed position. It's not moving up and down, it's fixed. If it's fixed, delta V is 0, that means no change in volume, that means constant volume, that means you have to use delta Q as equal to NCV delta T. NCV delta T, and let's say delta T is in this case is delta T2 and in this case delta T1 here. Since it's both, it's equal, so we can use, this is, let's say this is first and let's say this is second, so we can say that 1 is equal to 2 NCP delta T1 is equal to NCV delta T2. From here, the value of this N can be cancelled out. You can find delta T2 as Cp by Cv multiply with delta T1. Now you see here, it says that two cylinders A and B fitted with piston contain equal amount of ideal diatomic gas. Diatomic gas, what is the value of Cp by Cv? That is gamma, that is 7 by 5. We can easily say that that's 7 by 5. Now you see here, if the rising temperature of the gas in A is 30 Kelvin, so delta T1 is given as 30 Kelvin, put Cp by Cv as 7 by 5, and I think that we can rub this, it's not no more required. So delta T2 is equal to Cp by Cv, that is 7 by 5, multiply with delta T1 30 Kelvin. So this will turn out to be 42 Kelvin, that is change in temperature of the second in container B is 42 Kelvin, option number D. So A, B, C will be incorrect and D will be the correct answer. Hope that you have understood how to solve this. It's a very good question. All this basic formula that we are discussing, and I have already explained in brief detail about each of the application, about how this formula have come, about monatomic gas, diatomic gas, their Cp, Cv, their relation with heat energy supplied, everything we have discussed in class. Hope that you are enjoying and learning with each of the questions that has been discussed, and it proves to be helpful for you all in the class and in your preparation also. Let's go question number 10. When an ideal diatomic gas is heated at constant pressure, ideal diatomic, again diatomic gas, so you can make out what things you should actually remember, Cp, Cv and the value of gamma. Let's see whether we need or that or not. Is heated at constant pressure, the fraction of the heat energy supplied which increases the internal energy of the gases. We need to find out what fraction of heat energy supplied increases the internal energy of the gas. So we all know that delta Q is equal to delta U plus W. This is from the first law of thermodynamics. What we require that what is the fraction of heat is supplied which increases the internal energy of the gas is. So what you can use? You can use delta Q is equal to NCP delta T. This is what we know, and delta U is equal to NCV delta T. We know this. I have told you in detail about all this. Once again, if you want, you can read this at constant pressure. So at constant pressure, the heat energy supplied will be NCP delta T, and we all know that the value of delta U is NCV delta T. You need to find out delta U by delta Q. delta U by delta Q. So NCV delta T by NCP delta T, and after so many discussion based upon CP and CV, I believe that you can clearly now answer this. N and delta T will be cancelled out, that will be same. Clearly the answer will be CV by CP, that is 1 upon CP by CV. And for a diatomic gas, just now I have put in the last question the value of CP by CV as 7 by 5 for a diatomic gas, and again it's a case of diatomic gas. So here you will be getting the answer as 5 by 7. So what fraction of the heat energy supplied will be used to actually change the internal energy, to actually raise the internal energy? That will be actually, it's 5 by 7 value of the heat energy supply that will be actually utilized in increasing the internal energy. So that option A 2 by 5 no, B 3 by 5 no, C 3 by 7 no, D 5 by 7. Now see, with all such discussions, what one thing now you would be having in your mind? You have to remember the value of Cp, Cv and gamma for monatomic and diatomic gases at least. And I have also told you in case of raised energy, in case of raised temperature at higher temperatures, what value of Cp, Cv and gamma you have to use, both for monatomic and diatomic gases. How Cv is related to degree of freedom, I have told you in detail how to find the degree of freedom for monatomic and diatomic gases, and even for diatomic gases with raised temperature with high energy. Next thing, after all this classes, after all this discussions, I believe that you would be thorough with the entire syllabus, with the entire chapter, with the entire concepts. In the next exercise, I will be discussing some more questions based upon JEE advanced pattern. Hope that you are mentally ready to practice it, and I wish you all the very best in your preparation. So thank you everyone for joining me here. We will meet in the next class with more discussions.